Okay. Well, let's remind ourselves what we are doing. We did define a homology theory using a set of axioms, and then we in the first couple of weeks we saw that those axioms alone allow one to calculate the homology of quite a number of examples, such as spheres, orientable surfaces, and so on, wedges, disjoint unions, and a homology theory is standard. Let's recall. Let's recall that a homology theory is standard when, if and only if, the homology of a point in non-zero degrees vanishes. But apart from standard homology theories, there are lots of other homology theories which aren't standard, and we will not be able to discuss those in detail, but let's just keep in mind that those theories actually do exist and are interesting. Now the question is, how does one check that those theories in fact exist? Well, we started constructing the standard homology theories, and let's briefly recall what we did. We did introduce a class of spaces which are the geometric realizations of simplicial complexes. And for each of those we saw how to define a chain complex of abelian group. And I said, I didn't prove, I just said that those chain complexes in fact compute the alpha. Also, we did discuss delta sets. Delta sets is a class of spaces which is larger than, actually, as a class of spaces, it's not larger, but let's say it's a class of combinatorial structures which is larger than simplicial complexes. As such, it is more flexible, and we saw an example for the two torus constructing a simplicial decomposition is tricky. It produces lots of simplices, and it's not very clear why the homology of the two torus is what we computed it to be. Whereas for delta sets, the chain complexes, there's more flexibility, and one gets chain complexes which are smaller and more tractable. Actually, the main reason why we consider delta sets is that in a short while, we want to consider singular homology, and then after that singular cohomology. And the singular chain complex is the chain complex of a delta set. And we will shortly see what this delta set actually is. And it's a delta set, it's not a simplicial complex. This is the main reason we actually mention delta sets at all. This delta set turns out to be at least weakly equivalent. This delta set is constructed from starting from a topological space X, and it is weakly equivalent to X. And if X happens to be a CW complex, for example, one can replace weak equivalence by just equivalence. Are there any questions? Does anyone remember what a simplicial complex is? It's just a set plus a family of subsets, and this family should be closed under taking subsets. And then starting from such data, we can construct its geometric realization in a straightforward way. Delta set is something similar, a bit more general, not much more general. In fact, as one can check, on the level of spaces, one doesn't really get anything new by considering delta sets. Why? If we have a delta set, we can always subdivide it to get the geometric realization of a simplicial complex. So what's new? We don't get any new spaces. but we get a new combinatorial structure on the spaces which are already covered by this example anyway. So everyone, or almost, and if you don't remember it, please let me know. But hopefully everyone remembers what a simplicial complex is. So we will not talk about those. But let's review delta sets. So the definition is, in fact, quite similar to the definition of a CW complex. We have a family of maps from. Sorry, this doesn't make sense. Does it make sense now?
Yes.
Okay. We have a family of maps from simplices into X. Well, the first property, the restriction of each of those to the interior of the N simplex. Again, and the dimension of the N simplex, N of alpha, only depends on alpha. Nothing more. The restriction is injective, and the images of the interiors cover everything. Does this make sense? And we saw a few examples at the end of last week's class. Well, second. What was the second condition? Does anyone remember? Well, there is the word affine somewhere, but X is not a subset of a vector space, so it doesn't really make sense to say that sigma alpha itself is affine. Any other suggestions?
Is it condition on topology of X?
Well, no. There will be one, but we also need a condition which says something about the restriction of sigma alpha to the boundary of this simplex.
Maybe the maximum boundary to simplex itself. Fine.
Well, the second condition says the following thing. Suppose we have the following map. First, we take the map from delta n minus 1 into delta n, the ith phase map. What does this mean? Well, this ith phase map is affine. So here is where we use affine. It takes vertices to vertices, and it preserves the order of the vertices. So affine. Okay, and as is easy to check, there is exactly one such map. So there is no ambiguity. There is one such map for every I. So let's take this one and compose it with sigma alpha. Our requirement is that this map is the same as sigma beta for some beta. So the resulting map from this simplex to X should be on the list of these maps. Well, let's recall instead of this example, let's consider another one which we haven't seen. So let's construct let's represent the two-sphere as a delta set. We did the two torus last time. Let's do the two-sphere. Well, let's take two copies of the triangle and label the edges as shown on the blackboard or the green board, as the case may be, and then we have
second triangle is empty.
say again?
Is empty.
What is empty?
The second triangle has...
No. Well, I just want to show that this is not the same triangle. Now we take two triangles, label the edges, and then identify both triangles using these identifications. And then we have a delta structure. How many elements will there be in A? In other words, how many simplices do we have altogether? Well, we have 7, no, 8. We have three zero-dimensional simplices, 2 one-dimensional simplices, no, 3 one-dimensional simplices, and 2 two-dimensional simplices. So 3 plus 3 plus 2. And this one is supposed to be delta 2. And there are 2 maps from delta 2 to the triangles, and there are delta 1 is a line segment, and we have 3 maps which are just basically given by the labelings of the edges, and we have we have three maps from the 1-point space delta node into X. So X in our example is this. Modulo the equivalence relation given by the arrows. Does this make sense? Please observe, we do not get a simplicial complex in this way. Why? Because we have two simplices, and their intersection is not a common phase. Their intersection is a union of 3 common phases. If this were a simplicial complex, the 2 simplices would have to coincide. But as is also clear from the picture, there is a way to subdivide this thing into simplices so that we actually get a simplicial complex. Are there any questions?
Can you illustrate the second condition?
Well, the second condition. Here we have a map from some standard delta 2 into each of those. Well, let's say the standard delta 2, let's say each of these two lives in R2, and the standard delta 2, let's say it also lives in R2, and just maps into these into each of these two in an orientation preserving way. Or even better, let's order the vertices 1, 0, 1, 2, 0, 1, 2, and let's order the vertices of the standard simplex 0, 1, 2. Then there is a unique affine map, blah blah blah. Okay, let me now take delta 1. And map it into this phase 0, 1, so that here we also have 0 and 1, and we require that 0 goes to 0, 1 goes to 1. And then I take this map, and or one of these two maps. And the requirement is that the resulting map is also on the list, meaning it's one of the orange maps. Are there more questions? Here is another equivalent way to think about delta complexes, which will come in useful in a few minutes. We could take the disjoint union of some number of simplices, maybe finite, maybe infinite, just basically an arbitrary union of simplices. And we introduce an equivalence relation which is generated by the following identifications. Okay, so okay, the equivalence relation generated by. Is this clear? Basically, we can always introduce some number of identifications and then take the coarsest equivalence relation, which identifies the elements which are glued together by each of these identifications. So this is just general nonsense. Okay, so okay, let me so let me put here n of alpha and this alpha means the following thing. We have for each alpha in A, we have some simplex delta alpha of dimension n alpha. Again, this is just notation. What is delta alpha comma I? Well, this is the ith phase. Anyway, ith phase. What does this mean? Well, this means the following thing. Each of these is a copy of the standard simplex, and the standard simplex has the ith phase, and here we take the ith phase in this sense, and then we identify the ith phase with the simplex beta of dimension n of beta for some beta in the same indexing set A, and this beta depends on alpha and on I. And this will be useful in a minute in order to construct, in order to realize the singular simplicial complex as the chain complex of a delta set. But actually, I realize now I have forgotten one thing that some, I think you, have already mentioned, which is the topology. We require that a subset Y of X is closed if and only if sigma alpha of Y inside delta n of alpha delta n of alpha, just because this is the standard simplex, is closed. Oh yeah, sorry. Yes, exactly. Thank you. And by the way, if A is finite, then this condition is automatic. Why? Why is this automatic when A is finite? Or maybe it isn't automatic. Let's think.
If we have such set whose image under all these maps is closed, then it consists of finite closed parts.
Well, yes. So the first step, if the frame is closed, the intersection of y with each image of sigma alpha is closed. Closed where? Closed in the image of sigma alpha. Why? Because sigma alpha as a map from the standard simplex to the image of sigma alpha is proper.
This condition is for regularly alpha.
Yes, it's closed for all alpha in A. Thank you. And then we use the fact that that a finite union of closed sets is again closed. Does this make sense? Okay, now let's see. So we know from this definition and from this example what a delta set is, sort of. Let's recall the chain complex, which is associated to a delta set. Actually, I don't remember whether or not we did it last time. Did we? Did we not?
Only for simplification sets.
Okay. Well, in this case, there is nothing to recall. Let's define the chain complex. Okay, is everyone familiar with chain complexes? Chain complexes of abelian groups. as a group, the degree n component of this thing is just 3 abelian generated by sigma alpha n, meaning it is generated by those sigma alpha such that n of alpha is n. Does this make sense? And then we need to define the differential. How? Well, okay, let me put it. I don't put an I here, although some people put minus I, sorry, I plus 1. Which doesn't really matter. Alpha, comma, I. Okay, suppose we have a map sigma alpha n, where n stands for the fact that this map goes to this map goes from sigma n to x. No, sorry, delta n to x. So suppose we have such a map, sigma alpha. Then when I compose this with the ith face map, I get a map from sigma n minus 1 to x. Does this make sense? And I denote the result by sigma alpha comma I, where I varies from 0 to n. Well, then I have, by the definition of a delta set, the resulting thing, the resulting map, is again one of the structure maps. It is some sigma beta from the list of the maps which together form structure of a delta set. Well, okay, so I am allowed to consider this as an element of Cn minus 1. And I take the sum of those for I from 0 up to n with the sign minus 1 to the ith. Which is quite similar to what we have to what we have for simplicial complexes. Again, exercise. Delta squared is 0. And this is quite straightforward. Basically, when we apply delta twice, we get a sum over the restrictions of this sigma alpha to to the faces of dimension n minus 2, and each face will occur once with the plus and once with the minus. Does this make sense? Okay. And same as for simplicial complexes, we define homology by taking the homology of this chain complex. Does the expression the homology of a chain complex make any sense? If not, please let me know. Okay, are there any questions? Let's not do any explicit examples, because even for the two torus, the complex, the chain complex one gets in this way is quite messy. The main problem with this definition and with the similar definition for simplicial complexes is that both definitions in fact involve some combinatorial structure. It is not at all clear why the homology, the way we defined it, only depends on the topology of X and not on the particular structure of a delta set we have chosen in order to make this definition. So we have used some combinatorial structure to define something, and miraculously it turns out that this gives us the right answer. Why? Well, let's briefly let's first briefly understand why this construction indeed works, and then we will decide whether or not we want to see the details. So why is this invariant under, well, homeomorphism or homotype equivalence or some other sensible equivalence relation? Let's see. I will now construct a delta set I will now construct a delta set starting from a topological space. X in this construction will be completely arbitrary. So the delta set will be in all interesting examples. The delta set will be quite large. The number of simplices will often be quite large. Well, quite large meaning literally there will be a continuum simplices of all dimensions. But it will not be possible to literally draw these delta sets on the blackboard. But they will still be delta sets. Okay, so well, to begin with, I take for each n the set of all continuous maps from the standard n simplex to x. So there are continuously many of those in most examples we're interested in. Now, I define the thing of x. How? First of all, I take the union of all, the union of many copies of the standard simplex. How many? Well, as many as there are elements in all ANs. But for each element of an AN, I take the standard simplex of dimension n, which sort of makes sense. Okay, so this is just a disjoint collection of simplices of varying dimensions, and the size of this thing is enormous, huge. Gigantic. Anyhow, so this part is clear. Now, what is this? Well, it's something we already saw quite a few times, but let's write it down nonetheless. So, okay, sigma, sorry, not sigma, tilde. Tilde is generated by identifying the ith phase of delta n sigma. Let's recall that delta n sigma is just another copy of delta n, the standard n simplex. So, generated by where sigma I is sigma composed with I phase delta n minus 1 to delta n. Okay, now so sigma small I is a map from delta n minus 1 to x. So it's an element of a n minus 1, and we identify this, and so we have the corresponding simplex delta n minus 1 sigma I. And we have this simplex. They are both simplices here. And we identify the ith phase of this simplex with this simplex. In such a way that vertices go to vertices, and moreover, the order of the vertices is preserved. Does this make sense? And more or less, by definition, the result is a delta complex. A delta set. It's enormous, yes, but it's still a delta set. Oh, sorry. Sigma x is a delta set. Now I want to construct a map from sigma x to x. How? Can anyone tell me how to construct a map from sigma x to x?
We have a map from every simplex to x, and it preserves
Exactly. Exactly. So suppose we have delta n sigma for every sigma here, and for every delta n sigma, we have a map from delta n, which is the same as delta n sigma, to x. Well, let me take the disjoint union of those maps. Those maps are compatible with the equivalence relation. So the whole thing descends to this whole collection of maps descends to a map from the Gaussian space. And it's a theorem by Milner, which is not very difficult, but it's not free either. The map this map is a weak equivalence. Which basically means it induces a bijection of the path components, and for each path component it induces an isomorphism of all homotopy groups with all base pairs.
What is weak equivalence?
Well, I've just said. Значит, как обычно, значит, биекция на компонентах связности, изоморфизм там всех гомотопических групп с любой отмеченной точкой для всех компонентов линейной связности. Well, we will not prove this theorem unless people want me to. I've just said it. It's a map which induces a bijection of all path components, a bijection of the sets of the path components, and an isomorphism of the homotopy groups for each path component, and for every choice of the base points.
Does it imply the homology groups are...
Yes, the homology groups and the homotopy groups, the singular homology groups, are the same, and the homotopy groups are the same as well. Okay, so as I said, it's not too difficult to prove this theorem, but let's unless people want to know the proof, we will skip it. Anyway, we will not even use the theorem, but this theorem serves as a motivation for the next definition.
I have a question here. So, how do you promise that a map in AN constructed induces the injection in the on the interior of
that? After we compose with this, of course it won't be. But on the level of seeing, just by more or less by construction, we build Sing out of a huge, enormously large collection of simplices, and then we make some identifications. But we always identify the interior of a simplex with some part of the boundary of a high dimensional of a higher dimensional simplex, well, it's more or less straightforward from the construction that we get to delta set.
And why it is Hausdorff?
Why is it Hausdorff? Let's see if there is a straightforward way to do this. Well, it's a good question, well, this is something one needs to check, and it would be a good exercise to do the checks. Well, the idea is suppose we have two. Well, the disjoint union of simplices is clearly Hausdorff. Suppose we have 2 points in the quotient space. Let's consider the preimages in the disjoint union, and well, the points are disjoint, so the preimages do not intersect. But the topology of the disjoint union is easy to understand, and let's consider several cases depending on whether the points belong to simplices of the same dimension or to simplices of different dimensions, and in each of those cases it's straightforward to construct two neighborhoods which are disjoint and invariant under the equivalence relation. This is the general idea, and one needs to check the details that it does indeed work.
If pre-image has the points in simplices of every dimension, for example?
Well, this could happen, but what helps here is that the identifications are always affine. We can't have arbitrary continuous maps. We can't use arbitrary continuous maps in the identifications. And let's introduce a metric on each of those simplices, and let's take we have two subsets of the disjoint union. They do not intersect. And let's take the standard metric on each of the simplices. The standard metric, what's the standard metric? Is the one that's induced from Rn plus 1. Let's assume, yes, so so the standard metric, those ith face maps preserve the standard metric just on the nose. Again, this is something you need to check. We introduce the standard metric, and then we could just take the epsilon neighbor. I think we could take just the epsilon neighborhoods of the sets, and this will do the trick. But again, this is something which is a good exercise, and I suggest everyone who is interested in this question tries to do the exercise along the lines which I have just sketched. And if it doesn't work, please let me know. Okay, are there any more questions? Okay, now let's define singular homology. Well, the singular homology chain, the singular chain complex. of a topological space X is the same as the associate the chain complex of the delta set sin X. Okay, let's have a break. I think do we or do we not deserve a break? Let's see. I think we're supposed to finish at 22, and the clock says it's 20 to 6. So unless the clock is wrong, we do deserve a break. Okay, let's have a 20 minutes break, and then we'll basically continue with this chain. No. Oh, it's better. Explicitly. Explicitly, Cn of X is the free abelian group on all sigma continuous map, a continuous map from delta n to X, and the differential delta is defined by this formula, and sigma I in this formula is the ith phase composed with sigma. And the first remark is C lower star of X, which is the collection of all Cn of X, is functorial in X, meaning by associating C lower star of X to X, we get a functor from topological spaces to complexes of free abelian groups. So this thing is definitely functorial, as opposed to this thing or its analogues. let me state the main properties of this functor. Property 1. Homotopic maps from X to Y induce chain homotopic maps from C lower star of X to C lower star of Y. Now, let's see if this makes sense. Well, homotopic maps from X to Y. Does this make sense? Induce. Does this make sense? Induce chain homotopic maps. This doesn't make sense. Okay, let's give the
obvious claim or is Newman theory?
no. Well, it's not obvious, but it's. Let me first explain what this means, and then I'll say a few words about the proof. Okay. Now, first of all, let's explain this expression, chain homotopic. What does this mean? Suppose I have, and by the way, I think if I don't know how many people have already tried doing problems from the problem sheet. 0, something like that. Anyway, there's a question there on chain homotopic maps. So suppose we have two chain complexes. And suppose we have F, well, let me just call them F and G, C1, C2, chain maps. What does this mean? This means both maps commute with the differentials. Does this make sense? F is chain homotopic to G if and only if, or if by definition. Okay, I want to erase this part. Is this all right with everyone? If I don't leave, there is there is a collection of maps going from each component of C1 to the component of C2 of degree 1 degree plus, such that so the let's see. Such that the difference f minus g in each degree is d delta plus delta d. Well, what does this mean? For example, in degree n, the difference of f minus g, where does it go? It goes from C1n to C2n. What happens if we apply d? We end up in, oh, sorry, this doesn't make sense, it goes in the wrong direction. Yes, sorry, I've mixed it up. Let me erase everything. And so the yes, so plus 1 plus 2. No, sorry. The only thing that I messed up was a minus here instead of a plus. This should be a plus. Then we do have dn, dn minus 1, and dn plus 1. So f minus g. In degree n, it goes from this group to this group. And the requirement is that the difference f minus g should be dn composed with delta, the differential of C2 in degree n plus 1, plus first the differential in C1 in degree n, and then dn minus 1. Does this make sense? Well, what are the properties? Well, one property is that chain homotopy is an equivalence relation.
I have a question. Should dn make the all diagram commutative or only this property for big D?
Well, what does it mean, all diagram? D, capital D, does not necessarily commute with F or G individually. So the second property if chain maps F and G are chain homotopic, then the induced maps of the homology groups are the same. Again, this is probably one of the questions in the first problem sheet. How to prove this? Is there any way to prove this statement? Yes, there is. But first, let me state two more properties of this functor, and then I will say something about the proofs. Second, and by the way, before we move on to the second property, it follows from this property of chain homotopic maps that what? That homotopic maps of spaces induce the same maps of the homology groups, of the singular homology groups, which is already something. Now, the second property. Suppose we have X suppose we have a space X, which is the union of the interiors of some family of subspaces.
Proper subspaces.
Not necessarily. Some subspaces. We just require that the interiors of those subspaces should be the union of the interiors should be the whole of X. Let's denote this collection of subspaces by U. Normally, this should be a fracture U or a calligraphic U, but I don't know how to do either of those. But so let's just say it's a different U. Anyhow. Now I want to define U small chains. What is it? It's a subcomplex of C lower star of X, where the nth component of the subcomplex is generated by those singular simplices such that the image is contained in some x alpha, maybe in several x alphas, but at least in one. Well, example. I don't know. Well, for example, this the yellow simplices would be U small, and the orange one will not be U small. Does this make sense? Okay. Now, the property I want to state is that the inclusion of U small simplices into the whole singular chain complex is a chain homotopy equivalence. Well, as an application, let's deduce the Meyer-Vittori's long exact sequence. Suppose we have a space X which is the union of two open subsets. And let's take calligraphic U to be the family U comma V. So the family has just two elements. We have the following long exact sequence, short exact sequence. Singular chains of U intersected V. Go to singular chains of U plus singular chains of V. Let's say we use a plus here and a minus here. And this map is injective, which is more or less by construction. What's the quotient? The quotient complex is exactly C upper U of X. Meaning the complex of chains which are U small with U equal to this family. So my claim is this sequence is exact. Okay, now first of all, does the word exact make sense? This simply means in each degree I have an exact sequence. Cn of the intersection goes to Cn plus Cn goes to Cn, and this should be exact. Okay, so everything's exact. And well, if you look at the sequence and remember the definitions, it's more or less straightforward that the sequence is exact. Does this make sense? Well, the non-trivial part is that this thing has the same homology as the whole of X, and this is where we use this property. Okay, does this make sense? If I have
I don't quite get why the last map is surjective.
well, suppose I have a singular simplex such that the image is contained either in U or in V. Well, suppose it's contained in U, then it comes from C of U. Okay. Are there any questions? So we have discussed two properties: homotopy invariance and small singular chains, meaning small with respect to some given family of subsets, such that the interiors cover everything. Okay, let's state another property, and this will be it. Suppose we have spaces, two spaces x and y, then the complexes C lower star of x tensor C lower star of y, and C lower star of x tensor y, x times y, the Cartesian product, are chain homotype equivalent. Okay, now let's see if we understand all the words. Well, first of all, we do understand C lower star of x and C lower star of y. Same for C lower star of x cross y. But what is the tensor product of two complexes? Does everyone know what I'm talking about? Okay, so, well, let's explain this. Suppose I have two chain complexes. Then I want to define the tensor product. It's another chain complex. I want to define the nth component. What will it be? Well, the nth component will simply be the direct sum for p plus q equal n, C1p tensor C2q. Where by tensor we mean the tensor product of abelian groups. Anyway, is everyone familiar with the tensor product of abelian groups? And well, the same works for modules over a ring. Basically, if the ring is, let's assume that the ring is commutative, then we could do the same for modules over a ring. Okay, now I need to define the differential. Well, suppose I have suppose I have an element of one of these summons. Moreover, suppose this element is the tensor product of something from C1 and something from C2. And then I set the result to be delta C1 delta 1 C1 tensor C2 plus minus 1 to the P C1 tensor delta C2 delta 2 C2 where where delta 1 is the differential of C1 and delta 2 is the differential of C2. Again, exercise, check that delta tensor, as I defined it here, squares to 0. Does this make sense? Do we understand now what the tensor product is? And well, if we want the differential to square to 0, we need to somehow correct the naive differential, which is just the differential delta 1 times the identity plus the identity times the delta 2. By the way, it doesn't really matter. I could have put a q here, or I could have put a p here, or a q. There are lots of ways to do this correction, and they all give the same result. The same result up to a natural isomorphism, which is again defined uniquely up to plus or minus 1. Anyhow, let's just choose some way of fixing the signs and then use it. Okay, do we understand now what this thing is? And well, similarly for this chain complex is something we know already. Okay, now. Now I want to write this as a slogan. It's more of a slogan than a mathematical statement, but nevertheless. All chain maps and chain homotopies in the three main properties, which are the first property, let's recall it, said that homotopic maps induce the same maps, induce chain homotopic maps of the singular homology complexes. Singular chain complexes. The second property was that the inclusion of the small chains into all chains is a chain homotopy equivalence, and the last one was was that these two chain complexes are chain homotopy equivalent, which means there are maps from this one to this one and from this one to this one, such that both compositions are chain homotopy equivalent to the respective identity maps. I didn't say it, but I'm saying it now. Okay, is everyone happy with what it says on the left board? Well, let's look at what it says on the right board. On the right board we have a slogan. It's not a precise mathematical statement. I didn't say, and I'm not going to say what in an appropriate sense means, because it basically in each particular case of these three, this is more or less self-explanatory, and if one starts to spell out the details, things get less clear, not more clear. So unless people want me to, I will just leave this as a slogan. Okay, now how to prove? How to prove all those things. There are two ways, which are essentially the same. First of all, one could do explicit calculations with singular simplices, and well, there's nothing wrong with that. And second of all, there is another way which is slightly more abstract, but on the other hand, it doesn't involve any explicit formulas and simplices, and this would be the acyclic model theorem. So the first method is explained in Hatcher's book. And I have notes which explain the second strategy. Now, my suggestion is, if there are people who want to know either the first or the second proof in detail, please let me know. If it's the first proof, I'll tell you where to find it in Hatcher's book, and if it's the second proof, I will send you my notes. And unless there are people who want me to talk about either the first or the second proof in class, let's just say that the first proof can be found here, the second proof can be found there, and we will not say anything about either of those ever again unless there are explicit requests from the public.
I have an explicit request about second.
Okay, so well, normally the second proof is a showstopper. Basically, if I explain it in class, people at some point will just stop understanding anything at all. So please send me an email, and I will send you my notes. It's short, but it's not for the faint of heart. Meaning, well, it's a bit abstract.
And what about the first part? I mean, from the Hatcher's book?
Again, if you want to learn this proof, I can simply send you the corresponding parts of Hatcher's book, and so my assumption is that, and moreover, it's not just an assumption; it's also my experience that most people do not want to know any of the proofs. And so for those who do, I will provide a reference or just some notes. В общем, практика показала, что каждый раз, когда начинаются цикличные модели, значит, это полностью отключает там почти всех присутствующих. Поэтому значит, давайте, значит, кому это интересно, я пошлю свои там, значит, записки, там все рассказано про эти цикличные модели. Ну, не все, но, по крайней мере, вот из того, что там рассказано, значит, понятно, как доказать вот эти пункты 1, 2, 3. Okay. Let's see. So we have how much time do we have? I think we have 20 minutes or so. Let's do one important thing. Which I sort of mentioned quite a few times, but we didn't talk about it properly. Relative homology. Suppose we have a space X and a subspace. A. Then C lower star of A is a subcomplex of C lower star of X, which is straightforward. Then the relative singular chain complex C lower star of x comma a is just the quotient complex. So we have an exact sequence C lower star of x goes to C lower star of, C lower star of a goes to C lower star of x, goes to C lower star of x comma a, and there are zeros on the left and on the right. Okay. Now, now we can define, we have a chain complex, so we can take the homology of this complex. And the result is something we call the relative homology groups of x mod a. And by construction we have a long exact sequence. Where we use h lower star of a to denote the h lower star, the homology of c lower star of a, and similarly for x. Well, let's use are we ready to apply this to anything at all?
Why sometimes we use reduced homology in this non-exact sequence? But now we use just homology, like reduced.
Well, if we have just homology, we can obtain reduced homology in two ways. Let's recall that we have this method which works for any homology theory. But there is another equivalent another equivalent way. We can take the singular chain complex and extend it one step to the right, where epsilon is the unique map from C node of x to z, which takes every generator to 1. So well, it's not very hard to check that these two recipes give the same result. Okay, now we have seen one application of small singular chains, which is the Maya-Vitoris long exact sequence.
Maybe a question or a remark here is that can we reproduce homology as a kind of relative homology, for example, taking A to be the point in X?
Sorry, the question is how to reconstruct
reduce homology as a kind of relative homology. For example, maybe we can take A to be a single point in X, and then we can reduce homology.
yes, but which point?
Which point?
If you take a different point, you would get a different group. This group will be isomorphic, but it will be different. If we want a functor which is defined on spaces, not pointed spaces, just spaces, then we need to use some abstract point here, which is not an element of x, just a point far, far away. Long time ago and far, far away. But if we want an invariant of based spaces, meaning a space is equipped with base points, then indeed there is a way to to take the relative homology mod the base point. Anyway, let me think. What is it that I want to do next? Okay. Well, let's do a quick. Let's briefly mention the excision property. This property follows from the fact that small singular chains are the same after a chain homotopy as all single chains. I'll explain how exactly it follows, and then we'll maybe calculate something using the excision property, but next time. So it's another application. Of small singular chains. Suppose I have X a topological pair. And suppose I have a B inside A such that the closure of B the closure of B is inside the interior of A. Then B can be excised. Now, what does this mean? Well, this means the homology of X minus B, comma A minus B the homology map of X minus A mod X minus B mod X minus B mod A minus B to the homology of X mod A is an isomorphism for all M. Well, let's see why this is true. Well, we need to find two subsets of X such that the interiors cover X. Well, let's see. One of those, well, it would be logical to take one of those as A. What about the other one?
B. X minus A.
Well, X minus A and A do not, rarely cover, the interiors rarely cover X, because then A would need to be open and closed, and this is rare. So what do we take? Yes, let's see, it's X minus B. Okay, so let's take U equal A comma X minus B. Let's see if it works.
G is an open set.
Not necessarily. But let's see if it works. So
Maybe we need to closure, X minus closure.
well, let's see. So we what is the interior of X minus B? Well, one guess would be that the interior of X minus B is X minus the closure of B. Well, is it true? Is it false? What do you think? What's the interior? Well, the interior is the largest open subset, which is entirely contained in X minus B. So we have this open subset. What's the complement? Well, the complement is the smallest closed subset, which contains B, and this is what the formula says. Basically, my claim is this is just the definition of the closure. The closure is the intersection of all closed subsets. The closure B bar is the intersection of all closed subsets which contain B. And the interior is the union of all open subsets which are contained in X minus B. Okay, well, let's see. We have this property, and this property says that B bar is inside the interior of A, which is the same as to say that X minus B bar X minus B bar contains X minus the interior of A. Well, X minus B bar is the interior of X minus B. So what do we have? the interior of x minus b contains x minus the interior of A. What does this mean? Well, this means if we have a point inside x which is not in the interior of A, this point should be in the interior of x minus b. So this thing shows that the interior of A union interior x minus b is the whole of x. So we are able to use the small chains argument. Well, let's see if it helps. Well, let me draw a diagram, and then we'll see which part, if any, of this diagram is any use. Let me take A minus B, x minus b, x minus b mod a minus b, 0, the same for a, x mod a, 0. And we want to show that this this thing is an isomorphism. Okay, let's okay. Well, let me replace I know I can replace x with cu of x, and then I get. By the way, I don't think we need I think we only need the last two rows. I don't think we need the first row. But anyway, let's forget about the first row for a minute. Let's focus on the second and the third. We have Cu of x, which contains Ca. What's the quotient? Let's see. Cu of x is as an abelian group is spanned by simplices which are entirely in A or entirely in x minus b. And then we...
How can we take a quotient by C?
Well, it's a good question. Well, this is a chain complex, and this is a subcomplex. And whenever we have a chain complex and a subcomplex, we can take the quotient complex.
It is subcomplex because we have an A in our collection.
Yes. Okay, so this what does this what is this complex? Well, my claim is this complex is in fact isomorphic to C x minus b mod A minus b. How? Well, there's actually a map in well, there are well, there are maps in both directions, but well, the one that's completely straightforward is this one. Suppose we have an element of C lower star of x minus b. Well, this is naturally an element of Cu of x. Now, suppose this element belongs. Let me draw. Okay. Now I want to. Okay, I want to draw the same row, but I want to draw it downstairs. I don't want to draw it upstairs. I want to draw it downstairs. 0 goes to C lower star of A minus B. C lower star of x minus b. And then I have the quotient complex C lower star of x minus b comma A minus b 0, and this map is an isomorphism. These maps are just some maps. They're not isomorphisms. They're not quasi-isomorphisms. They are just some maps. But the one on the right is not just a quasi-isomorphism, it's an isomorphism. which can be seen by just looking at what happens with basically this complex and this complex as abelian groups have natural bases which correspond to singular simplices which are in x minus b but which are not contained in a minus b. As an abelian group, C lower star of a comma b, not as a complex, as an abelian group, C lower star of x a as an abelian group, C lower star of x comma a is generated by those singular simplices such that the image is not entirely contained in A. Partially, maybe, but not entirely. And so this group, as an abelian group, this thing is generated by those singular simplices in x minus b, which are not entirely contained in a minus b. And this group has a basis which is exactly the same. What do we have? We have singular simplices which come from A. These have been quotient out. So what remains is singular simplices with which come from from x minus b. And we quotient out those which come from A. In other words, which come from A minus B. So as abelian groups, these two are the same. And from the diagram we see that we have a chain map from this one to this one. Okay, I've run over time. There is no denying it. We're quarter an hour late. So sorry about that. Anyhow, this is how one deduces the excision property from small singular chains. Are there any questions, remarks, comments, objections, etc., etc.? Okay, well, I think enough is enough. Let's call it a day.